Welcome to this video. I'm Sneha George, Assistant Professor from Computer Science and Engineering Department. In this video, we are going to see the fifth experiment of the operating system lab, which is a critical section problem. So we'll be detailedly learning about the various critical section problems, learn about what a critical section is about and what are the tools by which you can synchronize. So to begin with, what a critical section is. Okay, so a critical section, for example, if one or more process want to access a same code segment, that code segment is a critical section. For example, or we can say that if there is a part of the program which it's actually a part of the program that wants to access a shared memory. So this is what is called as critical section. So let us consider n processes, okay? So P0, P1, P2, up to Pn minus 1. Let us consider there are n processes. Each of these process has a critical section segment of code, okay? So here the process will be able to change their common variables. They'll be able to write into the file, update the table, etc. Okay. So the major thing that you have to see to here is that when one process is in the critical section, no other process may enter the critical section. Okay. So every process will have to ask permission in order to enter the critical section. For example, there are three processes, P1, P2, P3, and P1 is a process which is currently in a critical section. Okay, when that P1 is in the critical section, P2 and P3 will not be allowed to enter the critical section. Okay, so let us see the general structure of a process PI in a critical section. Basically, there are three sections. Okay, first one is the entry section, second is exit, and the remainder section. Okay, there are three sections that may fall in the critical section. Okay, so generally a process, what the process PI, it will enter first into the entry section. Okay, every process, the process gets into the entry section. After getting into that section, it will go to the critical section. It will be in the critical section. So during this particular, for example, P1 is in the critical section. Okay, in such a case, P2 and P3 wants to get inside this critical section. It is not possible. Okay, only once P1 comes out of the critical section, then only the other process can enter. So first the process PI will enter into the, for example, P1, it will enter the entry section, then it will execute the critical section, then it will come out of the critical section and finally execute the remainder section. Okay, so there are three sections: entry, exit, and remainder. In between we have a critical section. So this is a general structure of a critical section. So there are actually solutions to the critical section problem. There are three solutions that we see. First one is mutual exclusion, second is progress, and third one is bounded waiting. So let us see what is mutual exclusion. If there are three processes, they should be mutually exclusive. That is, if the process PI is executing in the critical section, then no other process can be executing in the critical section. As I already said, if there are three processes, P1, P2, and P3, if P1 is executing its critical section, then P2 and P3 has to wait till the finishing of the P1's critical section. Okay, until and unless P1 completes its critical section, it cannot, the P1, P2, and P3 cannot enter its critical section. So that is what is called as mutual exclusion. Second solution is progress. So progress, to see to the definition, if no process is executing in its critical session and there exists some process that wish to enter the critical session, the selection of the process that will enter the critical section next cannot be postponed indefinitely. So progress means currently there is, for example, P1, P2, P3, currently there is no process executing in the critical section. In such a case, you can give chances for the process to enter into the critical section and execute the critical section without postponing indefinitely. So that is what is called as progress. Third one is bounded waiting. Okay, so bounded waiting, in that case, a bound must exist on the number of times that the process are allowed to enter the critical session after the process had made a request to enter into this critical session and before that request is granted. So whenever a process is waiting, you should always have a bounded waiting. You should not keep that process wait indefinitely, okay, infinitely. You cannot make them wait for a longer period of time. That is what is called as bounded waiting. So these are the three solutions to the critical section problem. Now let us see how to implement. So this is called as semaphore. So semaphore is actually a synchronization tool, okay, which will allow the process to synchronize their activities. So the semaphore has, it's actually an integer variable. Let us name it as S. And the semaphore is an integer variable and has basically two atomic operations, okay. The two atomic operations, that is, one is wait and the other one is signal. These are the two atomic operations that can be performed by a semaphore. Okay, semaphore is nothing but a synchronization tool, which is actually a integer variable. Okay, so this wait and signal, it is originally called as P or V. You can say it that way also. Okay, now let us see to the definition of wait operation and signal operation. Okay, so wait operation and signal operations are the two atomic operations that can be performed by a semaphore. So wait operation, you can see the semaphore integer variable is decremented, okay, whereas in signal operation the semaphore integer variable is incremented. Okay, inside wait operation it is decremented and inside the signal operation it is incremented. So let us see the types of semaphores. Okay, there are two types of semaphores. First one is counting semaphore and second one is the binary semaphore. Okay, it is same as that of mutex lock. Binary semaphore, from the name itself we can say that this semaphore will have an integer value which will be ranging only 0 and 1. Binary values 0 and 1. Okay, binary semaphore, it will have only values zeros and 1. Whereas counting semaphore is an integer value where your value can range over an unrestricted domain. For example, the value can, it's a counting semaphore, right? So it can range from 1 to 3 up to n. Okay, so these are the two types of counting semaphores. Now let us see the various classical problems used to test newly proposed synchronization schemes. Okay, so here in this experiment you will have to develop programs for these three problems. Okay, these are the three classical problems of critical session. First one is bounded buffer problem, or we call it as producer consumer problem. Second is readers and writers problem, and finally dining philosophers problem. See, these are the three classical problems that you have to understand. Okay, so first let us see what a bounded buffer problem is. So bounded buffer problem is otherwise we call it as otherwise we call bounded buffer problem as a producer consumer problem. Okay, so producer is producing an item and consumer is consuming an item. Okay, so when a producer is producing an item, okay, the consumer has to wait till the producer finish producing, okay, and vice versa. Okay, in case if producer is producing, the consumer has to wait till the producer produces, and if the consumer is consuming, then the producer also will have to wait till the consumer finish consuming. Okay, so in this bounded buffer problem, we consider there are n buffers. Okay, we say there are n buffers and each buffer is capable of holding a item. Okay, so in this problem we introduce three semaphores. First one is mutex, second is full, and third one is empty. The full and empty, they are called as counting semaphores. Okay, and mutex is the semaphore which is a binary semaphore in this problem. Okay, sorry. So mutex value is initialized to the value 1, full is initialized to 0, and empty is initialized to a value n. N value can be any value of your choice. Okay, so because we said there are n buffers and each can hold one item, So we come across three semaphores, one is mutex, full and empty. Out of these three semaphores, mutex is a binary semaphore and full and empty are the counting semaphores. Now let us see to the code and to an example. So this is a code for producer process. This is a code for consumer process. Before coming into this, we will see an example and understand, and then so that you will be much more easier to understand the code. So let us see the producer part. Okay. So we have a producer and also a consumer. Okay. As we said, we have a binary semaphore, which is a mutex, which is initialized to 1. Okay. So mutex is equal to 1, which means that your buffer is not being used by anyone. Now, full is initialized to 0 and my empty value is 6. Okay, so here it is a producer. So producer wants to produce. So now the producer will go to the buffer. Okay, it will go to the buffer so that it will check the mutex value. So it sees that the mutex is 1, which means that buffer is not used by anyone. So it will change, it will now make the mutex value to 0. It's going to start producing. So automatically, if the producer is producing, the full becomes 1. That is, your full value is incremented, which means that this is actually the signal operation that is carried out by this. Signal of full, it becomes signal of full, and weight of empty. So empty becomes 5. Okay, now the producer is producing. When full is equal to 1, the producer started producing. Okay, now what happens? Now what happens is the consumer checks for the mutex value, and consumer sees that the mutex value is 0, which means that the producer is producing. Okay, or else we can say the buffer is used by producer. Okay, so in such a case, the consumer will have to wait till the producer finish the producing. Okay, so this is a case with producer process. Now let us see to the code of the producer. As we said, structure of the producer process. So first is weight of empty and weight of mutex. First one is weight of empty and weight of mutex. So weight of empty. So initially the mutex value was 1, empty was 6. Okay, you have seen the diagram. Mutex value was 1 and the empty was 6. Then the mutex value became 0, then the empty value became 5. Okay, so after that the producer started producing. So it is signal of mutex and signal of full. So when the mutex value became during the production by the producer, signal of mutex, so the mutex value is 1 and the full value is 0. When the full value is 0, the full value is 0, the mutex, sorry, the when so once the process producer started producing, it becomes signal of mutex and signal of full. So mutex is 1, full is 0. Mutex is 0, the full is 1. Okay, so this happens with the producer process. Now let us see to the consumer process. Okay, this is what we have seen the producer. Now coming to the consumer, let us see there is a consumer and then the producer. So what happens? First, the mutex value is 0. So which means that the buffer is empty. It's not being used by, buffer is not being used by anyone. Producer is full and empty becomes 2. Now what happens? We are making it mutex value to 0, full to 3 and empty full to 3. That means when full becomes 3, what happens? It is actually weight of full that is happening. Okay, so that means the consumer started consuming. And then the empty becomes 3. Empty becomes 3, that is signal of empty. So this is how the consumer is consuming. Now what happens? Producer will check for the mutex value. It sees that mutex is 0, which makes the producer understand that the consumer is consuming. So the producer will wait till the consumer finish the consumption. Okay, so this is with regard to consumer and the producer processes. Okay, Now there is another problem. We've seen the three classical problems. First was the producer and the consumer problem. Second is the reader-writer problem. Sorry. So in reader-writer problem, a data set is shared among a number of concurrent processes. Okay, readers, okay, only they read the data set and they do not perform any updates. Writers, when you consider writers can write as well as read. Readers can only read, they cannot do any modifications or any updates in the data set. Okay, so the problem is it will allow multiple readers to read at the same time, but at a single time, only one writer can access the shared data. Okay, so if you have a reader, if there is only one reader, if there is only one reader, if then any other readers come, you can perform the read. But if a writer comes, you cannot perform the write, because the write operation always writer can always give changes to the or give modifications or updates. Okay, so here we have three semaphores. Okay, as in the previous, like in the previous example, here we have three semaphores. Here one is write, WRT, write semaphore, mutex, and read count is a integer value. Okay, so these two semaphores, write and mutex, these are two binary semaphores. Write value is initialized to 1 and mutex is initialized to 1. Okay, then you have an integer value, as I said, which is named as read count, which will be initialized to 0. So let us see to the examples. In readers writers problem, the problem is that, for example, if the process P1, there is a database and it is performing a write. If there is another read or writer coming, then it will not be allowed to perform. Why? Because P1 is currently doing a write. At the same time, if P1, P2, P3 are three processes, P1 is performing read. If some other process coming, some other reader or writer comes, reader will be allowed. Okay, read action can be performed, but write won't be allowed. So this is a reader writer problem. Okay, so if there are three processes, P1, P2, and P3. Okay, P1, P2, P3. If P1 is doing a read, P2 and P3 will be able to read. Okay, so the reader count will be 3. All the three can read at the same time because there is no updation or changes that is happening in the data set. Okay, so you have to keep track of read of more than one process at a time. Okay, so let us see, this is a structure for write process and this is a structure for read process. Okay, so here see, in the case of writer process, what is coming is first, as far as we said, there are three semaphores. First one is write, then the mutex, both are initialized to 1. So it is saying weight of write. Weight of write means the write value will be changing the value from 1 to 0. Okay, initially it was initially WRT semaphore was initially 1. Since this instruction is C, it is given weight of WRT, which means it is WRT has changed the value from 1 to 0. Okay, so once that is done, what does it mean? It means that the writing is performed. So now if a reader comes and check, okay, the write semaphore value or WRT value is 0, which means that the process is in the write, and so that the reader will have to wait till it finishes writing. So after the write is finished, then it will signal the write value. It will become 1. That time you can go for the reading process. Next, coming to the structure of a reader process. Okay, initially, as we said, the mutex value, a write value is initialized to 1 and the read count is 0. So it is saying weight of mutex. So mutex value will be here in the code. It is first telling weight of mutex. So weight of mutex means mutex value will change from 1 to 0. Then it says that read underscore, sorry, that is read count plus plus. So read count value was initially 0. Now it is changed to 1. So it says that if read count is equal to 1, then you have to wait, right? So the write value becomes 0. Okay, then you have to signal the mutex value. Okay, so in that case, you will have your reading being performed. Okay, in such a case, for example, in the meanwhile, if a writer is coming in and checking the value of write W value, it is now 0. Okay, so it will now wait another read comes, checks the value. So since because it sees that the value of write is 0, it will not be able to write, since it is reading, it is currently reading, but then it cannot write. Okay, since the value is 0. So it will wait for another reading process. It will again check for if the read count is 0. It will go for signal write and signal mutex. Okay, so it is simple as it is. You have to understand how the semaphores are initialized first. Okay, first it is initialized, mutex is initialized to 1, and the write is also initialized to 1, and the read count is 0. So when a reader process is carrying out a reading operation, mutex and the write will be turned into 0, and the read count will become 1. So at that time, if a write operation comes, it will not be able to write because it is reading. Okay, it will not allow, the write has to wait. At the same time, if read comes, it will check for that. Okay, if the read count is 0, then it will again allow you to read the process. Okay, now the last one is the dining philosopher's problem. Okay, so normally philosophers spend, as said in the theoretical aspect, philosophers already spends their lives thinking as well as eating. Okay, alternating thinking and eating. Okay, they don't interact with the neighbors. Okay, here they say that occasionally they try to pick up the 2 chopsticks one at a time. Okay, so in case of 5 philosophers, you, for example, let us see how the example is all about. You have as seen in this particular, sorry, as seen in this particular diagram, you can see there is a round table, a ball of rice kept in the middle, and there are 5 philosophers around the table. Okay, and if this is philosopher 1, this philosopher, if this philosopher want to have rice from the ball, this philosopher requires 2 chopsticks to be taken. Okay, if this particular philosopher 2 wants to have, it has to take the chopstick from the first philosopher as well as the this. Has to get the 2 resources. So let us see how this example. So this is a bowl of rice which is kept in the middle. There is 5 philosophers, P1, P2, P3, P4, and P5. And each philosopher will have to use a pair of chopsticks to have the rice. Okay, so this is chopstick 1, 2, 3, 4, and 5. There are 5 chopsticks. So if the process P1 want to have a rice, okay, if P1 want to have rice, then P1 has to have 1 and 2, the chopsticks 1 and 2 to have the rice. Okay, so if P1 want to eat, it has to have the chopsticks 1 and 2. Okay, at the same time, if P2 wants to have the rice, it has to have the chopsticks 2 and 3. But it cannot have the rice when P1 is having the rice. Why? Because P1 has taken the chopstick 2. So it will not be able to have the rice. So in such a case, P3 will be able to eat because it can take the 2 chopsticks 3 and 4. So at the time, only 2 philosophers will be able to have the rice because other philosophers will not have sufficient resources to have the rice. Okay, so let us see the code for this. Okay, so your structure of philosopher I is weight of chopsticks of I. So if the philosopher 1, if it is philosopher 1, weight of chops. So for example, here we say that in the diagram, we say that there are 5 philosophers and each philosopher will have 2 chopsticks to have. So initially, all the chopsticks will have the value 1. Okay, that is the chopstick semaphore is initialized to 1. So let us see to the code. Weight of chopstick of I, which means weight of chopstick of the first philosopher. So weight of chopstick, initially the chopstick value is all 1. So automatically weight of chopstick of 1 is 0. Then weight of chopstick of I plus 1 modulus 5. So first philosopher I value is 1, 1 plus 1 is 2, modulus 5 is 2. Okay, so the first philosopher will have to use the two chopsticks, one and the two. Okay, they can use the two chopsticks to eat. So that is weights of chopstick of I and chopsticks of I plus 1 modulus 5. Okay, so that is the problem with regarding to the dining philosopher's problem. So we have seen to the three problems of classical problems of uh, synchronization that is used to test newly proposed synchronization schemes. So the three problems that you come across is bounded buffer problem, reader writer problem, and dining philosopher problem. So you will have to code the programs based on the theoretical ideas that is being given and the examples being given, so that you will be able to code for these three problems. So hope you've understood this particular video. Thank you. Thank you once again.